Good morning, everyone. My name is Younes Ledmaoui, a PhD student at the Hassania School of Public Works in Casablanca, in Morocco. And today I will be presenting a systematic review on solar plant predictive maintenance. So, our focus will be on how predictive maintenance techniques have advanced in recent years, specifically in solar energy systems. The structure of this presentation is organized as follows: introduction, method, results and discussion, and finally conclusion and future work. Photovoltaic plants typically implement both preventive and corrective maintenance strategies. However, despite ongoing efforts, progress in developing more efficient and cost-effective methods has been slow. This presentation explores the growing role of predictive maintenance in extending the lifespan of solar panels, reducing downtime, and improving overall system performance through real-time data collection and analysis. This diagram provides an insightful categorization of the different types of faults that may occur in photovoltaic systems. These faults can be broadly classified into three primary categories: physical, environmental, and electrical faults, each further subdivided into specific types. The first, physical faults, relate directly to the PV panels themselves, divided into internal faults, such as damages within the PV cells; external faults, including cracks, broken panels, and degradation of the PV system. Secondly, we have environmental faults, for example, permanent shade faults. This results from long-term obstructions like bird dropping or dust accumulation. We have also temporary shade faults. The third classification is electrical faults. These faults affect the electrical components of the PV system and include array faults and power conditional unit faults. So each fault type has its own impact on system performance and requires a specific maintenance approach. Predictive maintenance techniques focus on several objectives for PV systems, including minimizing downtime, extending equipment lifespan, reducing operational costs, and improving energy efficiency. Predictive maintenance enables data-driven decision-making, allowing more efficient allocation of resources and better planning of maintenance tasks. A SWOT analysis of recent research reveals several strengths, weaknesses, opportunities, and threats related to predictive maintenance techniques in solar systems. Papers published after 2017, those with over 10 citations, have been reviewed to determine how well predictive maintenance has been adopted in the solar energy industry. We will now analyze how each of these factors shapes the development of predictive maintenance technologies for solar plants. Predictive maintenance leverages connected sensors to collect real-time data from PV systems. This data enables early detection of anomalies and facilitates timely intervention. Technologies like IoT and machine learning enhance the effectiveness of predictive maintenance strategies by optimizing maintenance workflows, improving both system efficiency and overall performance. Recent years have seen considerable advancements in predictive maintenance techniques for PV systems, driven by developments in IoT, machine learning, and deep learning. These innovations provide real-time anomaly detection, performance optimization, and fault prediction, contributing to a more sustainable and efficient operation of solar energy systems. This figure highlights 5 advanced methods for predictive maintenance in photovoltaic systems. emphasizing the growing integration of technology and AI to improving system efficiency and fault detection. Each technique is aligned with specific advantages and opportunities for enhancing PV maintenance. The first is drone detection. Drone offers a versatile solution for aerial monitoring for PV system installations. Thermal detection. Ground-based thermal cameras are commonly used to detect overheating components in PV system. The third method is machine learning that plays a critical role in analyzing vast amounts of data collected from the PV systems and enables automatic fault detection and performance optimization by identifying patterns that would be difficult to detect manually. However, it requires significant labeled data to train models effectively. The fourth method is deep learning. Building on machine learning, deep learning techniques delve deeper into data patterns, detecting more complex issues within PV systems. And the last method is monitoring analysis. So IoT-based real-time monitoring systems continuously gather and analyze data from the PV systems, providing immediate alerts for any anomalies. Each method offers distinct opportunities for enhancing the efficiency and reliability of PV systems, and combining these techniques, such as IoT with machine learning, can lead to even better prediction maintenance outcomes. The table presents a detailed review of 5 key methods applied in recent research for photovoltaic predictive maintenance. These methods include drone detection, thermal detection, machine learning, deep learning, and monitoring analysis. Studies like ENRI and QMR have integrated drone technology for automatic fault detection in PV modules, while others, such as Lee, use thermal imaging combined with deep neural network for precise temperature-based fault identification. A significant trend is the use of deep learning and machine learning models, as highlighted by Tang and Hong, which demonstrate enhanced accuracy in identifying defects through image and data analysis. Finally, papers like Emamian and Debanditi emphasize the role of intelligent monitoring systems that leverage IoT technology and artificial neural networks for predictive maintenance, enabling continuous real-time analysis and proactive fault management. In this table, we can observe that drone detection is utilized in 4 articles, with thermal detection featured in 4 as well. Machine learning approaches are applied in 7 papers, while deep learning techniques are leveraged in 8 studies. Additionally, monitoring analysis appears in 6 articles. The consistent use of machine learning and deep learning across the majority of the papers highlights their growing importance, particularly when combined with real-time monitoring solutions for enhanced predictive maintenance. These methods offer the most comprehensive and effective solutions for detecting and preventing faults in photovoltaic systems. Choosing the right predictive maintenance technique is crucial for optimizing both system performance and cost. Drone inspections through comprehensive are costly, especially for large-scale installations. Ground-based thermal inspections are more affordable but lack the extensive coverage drones provide. So IoT-based monitoring systems involve setup and maintenance costs but offer long-term savings through real-time fault detection and reduced manual inspections. Table 2 provides a detailed cost comparison for each method. Table 3 outlines the strengths and weaknesses of the five key predictive maintenance methods discussed. Combining methods such as using IoT monitoring alongside machine learning can yield better results by addressing the limitations of each approach. This hybrid strategy improves system reliability and fault detection by leveraging real-time data and predictive algorithms. The reviewed methods clearly show that while individual approaches like drone detection or deep learning offer significant benefits, the most impactful solutions come from combining continuous monitoring with machine learning techniques. For instance, Imamium and Dependency demonstrate that integrating real-time monitoring system with machine learning models, such as artificial neural networks, allows for more accurate and timely detection of anomalies. This combination enhances the system's ability to predict faults before they escalate, ensuring better efficiency and longevity of PV systems. Therefore, it's clear that harnessing the power of both monitoring and machine learning is the most beneficial approach for proactive and effective predictive maintenance. Our research evaluated various predictive maintenance techniques, including drone and ground-based thermal inspections, IoT monitoring, and machine learning. Each method has distinct advantages and limitations. For example, drone offers comprehensive views but are expensive and weather dependent, and IoT system provides early anomaly detection but require ongoing data management. So in conclusion, this review thoroughly evaluates predictive maintenance techniques for photovoltaic systems, encompassing drone and ground-based thermal inspections, IoT monitoring, machine learning, and deep learning. It emphasizes the selection of appropriate methods considering data availability, financial constraints, and real-time monitoring needs. Ground-based inspection offer cost-effective maintenance, while drone inspection provide superior aerial views despite weather constraints and higher costs. IoT monitoring detects anomaly early but requires careful data security management. Deep learning excels in fault detection, while machine learning focuses on pattern interpretation. Necessitating high quality data, future research should focus on developing scalable and cost effective predictive maintenance solutions that can be applied to solar energy systems globally. This will ensure that solar energy continues to play a critical role in the renewable energy landscape. Thank you for your attention.